Consider feeding this signal into a pair of inverters. If these inverters were ideal, then the output should look exactly the same as what went in, because the two inverters cancel each other out. However, it is impossible for information to travel faster than the speed of light, so there has to be a delay between when the input changes to when the output changes. In a still an idealized model, but one with a delay, we might expect that the output is just going to change after a certain period of time, and this is essentially a good approximation. When we study inverters at a lower level, we will find out that actually the voltage gradually rises until it gets to the top here. And so we actually have two regions. We have a small region here when the input has changed, but the output still hasn't reacted yet. Then we've got a gradual transition, and then we reach the point from this point onwards, the output is correct. And these two regions are very important for the study of digital systems, and as will be explained in a second, this one is called the contamination delay, and this one is called the propagation delay. In a more general situation, we have an arbitrary combinational logic circuit. It may have many inputs. Let's just consider a single output. And we assume the system's at equilibrium. So whatever the two inputs are, we assume that they have been constant for a sufficiently long period of time, that the output is constant, and there are no internal dynamics going on. And then we can ask the question, what happens if one or both of the inputs suddenly change? Well, the same thing as before is going to happen. The output is initially not going to change because it's impossible for information to travel faster than the speed of light. So there will be a period of time when the input's changed, but the output has not changed. Then we may have a gradual transition. We may have glitches. We may have funny things happening. But eventually, the output is going to be the correct value, and it's going to remain the correct value. And so for any logic circuit, we can give two numbers. We start the clock when the input or inputs change. The period within which the output is guaranteed not to change is called the contamination delay. Now, we can't work out the common contamination delay exactly because it depends on the temperature, on the output loading and things. But if you go to a data sheet, it will give you a bound on the contamination delay. So it's a promise or a guarantee. If the contamination delay is 2 nanoseconds, then that is a guarantee by the chip manufacturer that if the chip is originally in equilibrium and then one or more inputs suddenly changes, then within the next 2 nanoseconds, the output is guaranteed not to change. And we'll see later in this course why it's useful to know that. Now, we also start the clock at the same time, so do not make the mistake of trying to add contamination and propagation delays. We start the clock at the same time. As soon as the input changes, we start our stopwatch, and the propagation delay is a guarantee by the manufacturer that within propagation delay units of time, the output is going to be correct. So this is propagation delay. And if the propagation delay is 5 nanoseconds, as found on the data sheet, then under the conditions in the data sheet, such as the temperature range, the output loading, and so forth, if the inputs were to suddenly change and then remain valid and constant, then within 5 nanoseconds, the output is guaranteed to be correct. Now, it's important that this is taken from when the input is valid. And in this simplified example, we have an exact transition here, which is why contamination delay and propagation delay are both taken from this region here. However, if we connect this circuit to another combinational logic circuit, we see that the output, it contains a period in here when we don't know what's happening. So I call this the unknown region. Maybe it's well behaved, maybe it's not. Maybe there are glitches, we don't know. And that means that the input to this second combinational logic circuit is not going to be an ideal transition, but rather it will be in two parts. We first leave the valid state to enter the unknown state, and then we exit the unknown state into the new valid state. And in this case, the contamination delay is counted from when the input first becomes unknown or first changes, and the propagation delay is counted from when the input becomes valid and remains valid. Let's examine this in more detail on the next page. Let's look to see how to draw the timing diagram for the output waveforms when we've got two logic gates here, or logic circuits in general. This one has a propagation delay of 4 nanoseconds and a contamination delay of 2 nanoseconds. This one has a propagation delay of 7 nanoseconds and a contamination delay of 3 nanoseconds. The propagation delay is always greater than or equal to the contamination delay, and only for idealized circuits can they be equal. For any real-world circuit, the propagation delay is going to be strictly greater than the contamination delay. Here we have the input waveform going in here at point A. We assume that prior to A, the logic circuits are in equilibrium. We've got steady outputs, and for simplicity, let's assume that the transfer function is just that the output's going to be equal to the input. Normally we'd have multiple inputs. We're going to have some more complicated calculation going on. Remember, logic circuits implement truth tables, but we're not going to worry about this here. We're just going to focus on the effect of the contamination and propagation delays. So at B, the output's been a steady 0 for a long time. The same for output C. The output's been a steady 0 for a long time. We mark the points of interest. That's when the input A changes. This is where input A changes again. We go step by step. So we first focus on the output B. Because the contamination delay is 2 nanoseconds, we know that even though A has changed, we will have a period of 2 nanoseconds when the output B remains constant. After 2 nanoseconds, we enter a period of unknown. We don't know what the output's going to be. It might be a nice transition, it might contain glitches, we just don't know. What we do know is that 4 nanoseconds after the input has attained its new valid input, the output's going to be correct. The input A becomes valid again just after the yellow dotted line. So 4 nanoseconds after that, the output B is going to be valid. So therefore this period here lasts for 2 nanoseconds, making the time from here to here exactly 4 nanoseconds, after which the output B is going to be valid. To summarize, in the first case we have a very sharp transition here. We therefore start our contamination delay timer and our propagation delay timer at the same point because of this very sharp transition. The contamination delay timer expires 2 nanoseconds later, and that's when the output B enters its unknown state. The propagation delay timer, it expires 4 nanoseconds after the yellow dotted line, which is right here, and that's when the output is going to be valid. After the propagation delay is up, assuming the input has been constant for that period of time, then the output is going to be given by the truth table. So, provided the inputs vary sufficiently slowly and we've waited long enough, logic circuits are fully described by their truth table. That's what we learnt in part 1 of this course. But during the time when the input first changes and the output settles down, we can have a transient response, and in our timing abstraction, we simplify it to a period when the output has not yet changed, a period when the output is correct, and in between we don't know and we don't care. We can build digital circuits without knowing or caring what's happening in this region in here. The next time the input changes is here, and we go through the same reasoning. For 2 nanoseconds, the output does not change. For another 2 nanoseconds, 4 nanoseconds minus 2 nanoseconds, the output is unknown. And then after 4 nanoseconds from when the input became valid, the output is now valid again. So from here to here is 4 nanoseconds. In order to work out the output C, we have to identify when the input to the second logic gate changes. So the timings of interest are here and here, and here and here. Indeed, to simplify this diagram, we can and should actually remove this yellow line here and this yellow line here, because while these yellow lines influence what happens to this logic gate here, all that matters for this logic gate is its input, not the input A. So for working out what's happening in C, the time points of interest are when B is transitioning and nothing else. Following the same procedure as before, we know that the output remains constant until the input changes. The input changes at this point in time, but due to a contamination delay of 3 nanoseconds, the output is going to remain constant for 3 nanoseconds past that point. The width of these two dotted yellow lines is 2 nanoseconds, so 3 nanoseconds brings us to this point here. So from here to here, this interval is 3 nanoseconds. After the contamination timer has elapsed, we enter a period of don't know, don't care. We remain in this period until the input has been valid for long enough for the output to also become valid. So if we look over here at B, this is when the input becomes valid again. We have to wait 7 nanoseconds after this point, and assuming the input does not change within 7 nanoseconds, we wait 7 nanoseconds from this point, and then and only then is the output C going to be valid. So from this point here, we have to wait 7 nanoseconds. This brings us to halfway between there and there. So this, if I'm not mistaken, is going to be 7 nanoseconds, corresponding to the propagation delay of the second logic circuit. And when we reach the 7 nanosecond mark, after the input has become valid, then the output is going to be valid and remains valid up until at least the next event at the input, like this. Notice that in the first case, the period of unknown was simply 4 minus 2, and that's because the input transitioned instantaneously from one valid state to another valid state. For this one, if the input transitions immediately, then the period of being unknown at the output would be 4 nanoseconds, but we see here it's longer. And it's longer because its input has got a period of being unknown. So if we add this period to 7 minus 3, which is 4 nanoseconds, we should get the length of this. Now that's just to check what we're doing. The basic rule to follow is what we've done before, the contamination delay and the propagation delay. But as a check, you should find that that's going to be true. So this period of unknown corresponds in this case to the minimum 7 minus 3, as well as the extra period that the input was in an unknown state. We now repeat the same thing. We've arrived at this point here. We know that the input has changed, but for 3 nanoseconds, the output remains constant. So this is 2 nanoseconds. Let's say that this is 3 nanoseconds. So from here to here is 3 nanoseconds. Then the output enters a period of being unknown. How long does it last for? Well, we look at when the input is valid again. This is when it's next valid. And 7 nanoseconds after that, the output is going to be the correct value, since that's what propagation delay is telling us. So to summarize, for the second logic gate, we start our contamination delay counter when the input first changes, and we start our propagation delay counter when the input stabilizes. Same at this point here. Start contamination delay from here, start propagation delay from here. Once the contamination delay has expired and before the propagation delay timer has expired, we have our unknown output. We now move on to another related topic. Let's assume that we now form a big logic circuit in yellow out of these two smaller logic circuits. And we want to work out the propagation delay and contamination delay for this big logic circuit. If someone is going to use this big logic circuit, they don't really care about the internal dynamics. They just want to understand how this big logic circuit performs. They want to know what is the contamination delay and what is the propagation delay. We're going to first work it out from the timing diagram, then we're going to give a simple rule for working it out without the need for computing these timing diagrams. Let's look at this transition here. The yellow logic gate, we assume, has been in equilibrium prior to this event. We have a nice clean transition at the input. When does the output first change? Well, we trace it down here and we see the output first changes at this point in time, and we have 2 nanoseconds here and 3 nanoseconds here. So it looks like the contamination delay is going to be 5 nanoseconds. And by the way, that's 2 nanoseconds plus 3 nanoseconds. For the propagation delay, this is when the input becomes valid. When does the output become valid? Well, it becomes valid over here. And what's the time from here to here? We see from here, 4 nanoseconds brings us here, and 7 nanoseconds brings us here. And so therefore the time from this transition to when the output's valid is 4 plus 7, or 11 nanoseconds, which by the way is 4 nanoseconds plus 7 nanoseconds, giving us a propagation delay of 11 nanoseconds. As good engineers, we should be tempted to look over here to see if we get the same numbers as before. It turns out that we do, but a word of caution here, at this point in time, the output is not yet valid. And what we really need to do to define these numbers carefully is we need to wait for both the input and the output to be valid before measuring them. So it's okay to measure them at this point in time, but over here the circuit hasn't yet reached equilibrium, so we should not really rely on any timings we get from this transition here. Even though things work in this instance, you do need to be careful in general. Anyway, we don't actually need timing diagrams to work out the aggregate contamination and propagation delays. We just have to think through it in the following way. The contamination delay tells us when the output first changes. If you like, a bus full of tourists arrives at point A and the tourists get out of the bus. Some people are going to be fast, some are going to be slower. The fastest people are going to arrive at the output after 2 nanoseconds. It's impossible for them to arrive any earlier because 2 nanoseconds is the contamination delay. So to work out the combined contamination delay, we want to work out when a busload of people arrive at A, when is the first person going to appear at C? When is the first change in the output going to be detected? And we know that we have a minimum change of 2 nanoseconds before we get here, or 2 nanoseconds before the first person arrives here. And then once someone arrives here, or once there's a change here, we then have another 3 nanosecond wait until someone arrives here, until there's a change here. Therefore, the combined contamination delay is simply 2 nanoseconds plus 3 nanoseconds, or 5 nanoseconds. By a similar argument, looking at the slowest person takes at most 4 nanoseconds to get here, and then takes at most 7 nanoseconds to get here. Therefore, the propagation delay is 4 plus 7, or 11 nanoseconds. Finally, let's consider a more interesting combinational logic circuit made out of 6 smaller logic circuits, each with their respective propagation and contamination delays. And so our input goes into both this logic gate and this logic gate. The output of this logic gate goes into both this logic gate and this logic gate, and so forth, all the way through to the output. And the question is, treated as a single logic gate from here to here, what is the overall propagation delay and the overall contamination delay? To find the contamination delay, we need to find the fastest path through this network. Remember, a busload of people arrives here. The fastest people will make it through each logic gate based on the contamination delay. We want to know when the first person comes out the other side. We need to find the fastest path. Now, for very big, complicated networks, then this is a problem that computer scientists consider how to solve. But for simpler networks like this, we can do it ourselves by hand. Let's assume the input changes at time t equals to 0 nanoseconds. Then after 3 nanoseconds, there's a change at this point. And after 1 nanosecond, there's a change at the output of the lower logic gate. If we look at this logic gate, although the first person arrives along this path at time t equals to 3 nanoseconds, someone arrives at this logic gate after just 1 nanosecond, because someone gets off the bus, goes through this logic gate in just 1 nanosecond, and arrives here at time t equals to 1 nanosecond. This label is not on this arrow, but it refers to the output of this logic gate here. So the input to this logic gate first changes at time 1 nanosecond. Similarly, the input to this logic gate down here first changes at 1 nanosecond. This input changes after 3 nanoseconds, but the first change occurs at 1 nanosecond. We now repeat for the next set of logic gates. We look at the input to this logic gate here. The first person arrives along this path after 3 nanoseconds, but the first person arrives along this path after 1 nanosecond. This label here applies to the output of this logic gate here and not necessarily to just that path here. So after 1 nanosecond, someone has walked along this path, through this logic gate, and up here, arriving here. After another 4 nanoseconds, 1 nanosecond plus 4 nanosecond, the first person exits here. Similarly, for the logic gate down here, 1 nanosecond, someone enters it, another 2 nanoseconds, so at time 3, t equals to 3 nanoseconds, we have someone coming out of this logic gate. This logic gate up here, the first person to arrive is at time t equals to 3 nanoseconds. After another 1 nanosecond, the person's exited at time t equals to 4 nanoseconds. For this logic gate here, the first person to arrive is not the one at 5 nanoseconds, but the one at 3 nanoseconds. at time t equals 3 nanoseconds, someone comes in. At time t equals to 6 nanoseconds, they exit. The first person to exit is at time t equals to 4 nanoseconds, making the contamination delay 4 nanoseconds. And if we want to find the path through the network, then we can solve for that by looking at all our timing here, and we see that the reason why the contamination delay is 4 nanoseconds is because someone can walk from here through this logic gate, that's 1 nanosecond, through this logic gate here, that brings us to 3 nanoseconds, through this logic gate here to 4, brings us to 4 nanoseconds. So the fastest someone can walk from here to here is 4 nanoseconds, and that's why it's the contamination delay. For the propagation delay, exactly the same argument, except we're now looking for the slowest person, not the fastest person. In particular, people start here at time t equals to 0 nanoseconds. The slowest person will have exited this logic gate here at 5 nanoseconds. The slowest person will have exited this logic gate at 3 nanoseconds. For this logic gate here, the slowest person to arrive is at time t equals to 5 nanoseconds. Some people have arrived earlier, but we care about the slowest person. That's 5 nanoseconds. At t equals to 5 nanoseconds, the last person enters this logic gate, and they will be delayed by another 8 nanoseconds, meaning at time t equals to 13 nanoseconds, the last person exits this logic gate. For this logic gate here, the last person to arrive is at 5 nanoseconds. After another 4 nanoseconds, i.e. at time t equals to 9 nanoseconds, the last person exits this logic gate. For this logic gate here, the last person to arrive is at 13 nanoseconds. They need another 2 nanoseconds to exit, so the last person exits at 15 nanoseconds. The last person to arrive at this logic gate is at t equals to 13 nanoseconds. They need another 5 nanoseconds to exit. That brings us to 18 nanoseconds. 15, 18, the last person leaves at 18 nanoseconds, making the propagation delay 18 nanoseconds. The path the slowest person takes is through here, down through here, and out here. And if we have a look at how long it takes 5 nanoseconds, plus 8 nanoseconds, plus another 5 nanoseconds, which gives us our 18 nanoseconds. That's the time it takes the slowest person to go through this entire network here.